All right. Good morning, everyone. Welcome back. I hope you all had a good break. I guess we had some decent weather, so maybe you could spend some time outside. So we are going to get back into the swing of things. So the usual updates are that we will have a homework due on Friday. We do have a pre-lab number 4, so please finish that before your lab number 4 starts for whatever section you're registered in. And then, of course, we've got our midterm coming up next class. So that's on Wednesday. It's a paper midterm. It's in person in this room during the regular scheduled class time. So the format of the midterm, there'll be 2 multiple choice questions, and then there'll be 3 long answer questions. And on the long answer questions, you should try to write out your solutions in as much detail as possible. Even if you don't think you got the right final answer, if you show your work and write down like some kind of logical reasoning, you can earn a lot of part marks by doing that. Okay, and then there are no tutorials this week. They will resume next week. So the sorts of stuff we were talking about before the break was capacitors, in particular these parallel plate capacitors, where we imagine 2 sheets of area A placed parallel to one another and separated by some distance d. We defined this quantity capacitance, and it was defined to be if we apply a voltage delta V between our 2 plates using a battery, for example, those plates will store some charge Q, and the capacitance is the stored charge Q divided by the applied voltage. So a large capacitor will store a lot of charge for a given fixed voltage, but if you reduce the capacitance, then for the same voltage, you will store less charge. We were also able to come up with the value of C for this parallel plate geometry. It was given by a constant epsilon naught times the area of the plates divided by that separation distance. And then the last thing we did before the end of the break, or sorry, before the start of the break, was to determine how much energy is stored in a charged capacitor, and we found that we could express it in 3 equivalent ways. And so the quantities that are involved are the charge, the voltage difference, and also the capacitance C. And so you just need to know 2 of those 3 quantities in order to figure out the stored energy in a capacitor. Okay, so what I want to do today is I want to start by kind of just getting prepared for lab number 4. Some of you will start that lab number 4 today. So here's what I want imagined. So, sorry, lab number 4. Okay, so one of the things you'll do in lab number 4 is you'll take a voltage source. You'll use, instead of a battery, a power supply, but it does the exact same thing. It's a source of constant voltage difference. And we're going to connect it across a wire. The wire will have a certain length. It'll be cylindrical in geometry, and it'll have a certain diameter. And so what it's going to look like is we're going to imagine connecting a battery across a, let's say, a cylindrical conductor. So you could just have in mind just a wire. That's all it's going to be. Cylindrical conductor or a wire. Okay, so we'll draw our cylindrical conductor or a wire like so. And then what we're going to do is we'll take a battery, we'll put one terminal at one end of the wire, and then the other terminal at the other end. Okay, so this battery has a positive and a negative terminal. It provides a voltage delta V. And if you remember, what we discovered about these potential differences is that electric fields point from high potential to low potential. And so what we have established for our wire is we put the positive terminal or the high potential terminal of the battery at one end. So on the left-hand side, we have the high potential. And then on the right-hand side, we have low potential. So let's just recall that electric fields point from high to low potential or voltage, if you like. So remember, we had this way of calculating potential differences. It was this integral of minus the integral of E dot dl. And so if E is non-zero over some length, then there must be an there must be a potential difference across your starting point and your end point. Okay, so fair enough. Then what that means is that inside our conductor, we have an electric field that points from high to low potential. Now, if you think back, you might wonder, well, I thought we talked about electric fields in conductors, and we said that the electric field is always going to be zero in a conductor. You have to remember that was only for a conductor in equilibrium. And so what we said about conductors in equilibrium is that there's going to be no net flow of the charge in that conductor, of the mobile charge. Here, if we force the potential difference across our conductor such that there is an electric field inside the metal of the wire, then that means that this is not an equilibrium situation. And if it's not an equilibrium situation, that means we can have the net flow of charge, and that net flow of charge is going to be the current in our circuit. So since the electric field is not equal to zero in our conductor, this is a non-equilibrium situation. And so that means that we can have a net flow of charge. So in a simple conductor like copper or aluminum or whatever other conductor you want to think of, it's actually electrons that are free to move around. And so if we populate our conductor with some electrons, so let's put an electron here and over here. So all these blue dots represent different electrons. I'm only going to draw a few of them. So there's all these negative charges that exist in this conductor, and we have an electric field that points from the left to the right. That electric field exerts forces on these electrons that are free to move around. Because the electrons are negative charges, the force on them is in the opposite direction of the electric field. And so they all are going to experience these forces that will be minus the charge of an electron times the electric field. And so they'll all experience these forces that are directed towards the left, and we'll have this net flow of charge, negative charge, from the right to the left. Okay, so the electric field in the conductor exerts forces on the mobile electrons, causing a flow of charge or a current. Okay, so what we can do is we can come up with like a more formal definition of current. And the way we'll do that is we'll imagine placing some imaginary surface that intersects our wire. So I will try to draw that. And so let's say I put my imaginary surface over here. And so we'll shade it in. And that's going to intersect our wire here. And so we'll shade in this thing. Okay, and what we're going to do is we're going to get a stopwatch out, and we're going to set a timer. And while we're counting time, we'll keep track of how much charge has crossed that surface. And so we'll count the total amount of charge, delta Q, that crosses our surface in time delta T, and the ratio of the two, delta Q divided by delta T, will tell us the current. So we imagine keeping track of the amount of charge, say delta Q, that crosses a surface intersecting our wire during, let's say, time interval delta T. Okay, so then what we'll do is we'll define the current as the following. We define the average current as, we'll call it, say, I average, is how much charge crosses our surface per unit time delta T. Okay, and so this is going to be, I will be the symbol for current. And so if we do a unit analysis, the units of current are the units of whatever delta Q is, the amount of charge. And so we'll measure charge in coulombs and divide by a time interval, the units of delta Q divided by the units of delta T. And so delta Q is in coulombs and delta T is in seconds. And so our units of current are coulombs per second. And that, as you probably know, is defined as a new unit. And so it's an amp. 1 amp is 1 coulomb per second. So units of current are coulombs per second, which is defined to be an amp. So this is 1 amp, or 1 ampere is 1 coulomb per 1 second. Okay, and so just to make note of it, is a 1 amp is quite a large current. So like in your devices, when you charge your phone or whatever, it's probably more like milliamps that are running to your battery as you charge your phone. Your house, for example, will have circuit breakers or fuses that will blow usually around 15 amps. And so if you're running like a hair dryer and your clothes dryer or something that consumes a lot of power, then you might blow a fuse if you exceed that 15 amp threshold. Okay, so that's the average current, just like the same way we would define the average speed of an object. You take the total distance divided by the time interval. If you shrink your time interval down into an infinitesimal time, then you can get the instantaneous velocity, for example, and the same thing, we can get like an instantaneous current by taking a very short time interval, delta T. So if we shrink delta T, and we take, say, the limit that delta T goes to 0, we can get the instantaneous current, which we'll just call I, so we'll drop the average subscript. And so I is going to be equal to the limit that delta T goes to 0 of this ratio of delta Q divided by delta T. But that's just the definition of the derivative. And so current is dQ dt. Okay, one other thing we should just make note of is it's a bit unfortunate, but it's the way things have been established. It's the convention. Current is the direction of positive charge flow. So in our conductor, where we have electrons, which are negative, going from the right to the left, current in the circuit would actually flow in the opposite direction. So current would be from left to right, and so we'd have our negative charges flowing in the opposite direction. So let's just make a note of that. So in circuits, current is the direction of positive charge flow. So you can have positive charge flow. For example, if you go to a particle accelerator where they're accelerating protons and smashing them into things, then you would say the current, if in that particle accelerator, would be in the same direction as the positive charge flow. But when you're flowing negative charges, like in a metal, in a conductor, then the flow of charge is actually in the opposite direction of the current. Okay, so for conductors, or for a conductor, it is electrons, which are negative, that flow. Therefore, the current is in the opposite direction of the electron flow. So if we go add current to our picture up here, we would say that the current in our circuit would be from left to the right. Okay, so that's fine. And so basically that's one of the things you're going to do in the lab. You'll have this long wire, you'll connect a power supply to it, and you will set a voltage, delta V. And then you will measure the resulting current using a little handheld multimeter set up to make current measurements. Then what you're going to do is you're going to take your same voltage and you'll apply it to a different wire. In the lab, what we're going to be using is always the wire that has the same material. So if it's aluminum wire, then we'll keep using aluminum over and over, and we'll keep using the same length of wire. We're just going to change the diameter of the wire, and we're going to see how do the measurements change when we change the geometry of the wire. So let's suppose, oh shoot, I want to change the color. Here we go. So let's suppose we connect the same battery or the same voltage difference to different wires. So as I said, in the lab, all you're going to do is change the diameter of the wire. But in principle, you could have different types of materials. So you could have a copper wire, you could have an aluminum wire, you could have a lead wire or something like that. So different types of material, or maybe they have different lengths or different diameters, and maybe you could think of other things you might be able to change, and so on. If you did that experiment, what you're going to find is every time you change one of those parameters, either the type of material, the length of the wire, or the diameter of the wire, we'll get a different current for the same voltage. So we will find that for the same voltage, we get a different current. Okay. So in order to make predictions about what current you would expect for a given wire, we define this property of a wire called resistance. So the resistance R of a wire is defined as So if you set up this experiment where you have a voltage or a battery connected across a wire and you measure the current, if you take the ratio of the voltage that you use divided by the current, that defines the resistance. So the units of resistance are the units of voltage, is V, as a volt. Current we just defined as this amp or coulomb per second. And so the units of resistance is volts per amp. And that is defined to be an ohm. And so this is an ohm is the pronunciation. The symbol is capital omega. It's a Greek letter, it's capital omega, and we call it an ohm. So 1 ohm is 1 volt per 1 amp. Okay, let's introduce the circuit symbol for resistors because we already have the circuit symbol for batteries and capacitors. So the circuit symbol for a resistor is, I think it's actually kind of a symbol that makes a bit of sense. It's this kind of squiggly, sawtooth kind of line. And so to me, what it represents is kind of like a tortuous path through a wire. So the more kind of wiggly the resistor, the longer it takes a charge to make its way through. And so the rate of the charge flow gives the current. So a large resistance is going to result in a low current, a small current for a given voltage difference. Okay, so the circuit diagram then for our wire connected to a battery is. All right, so I'll just draw what we had before. So here's our cylindrical conductor. We connected this to a battery. We're already using the circuit symbol for our battery. What that's going to become then is we'll keep our battery the same. We'll just replace our cylindrical conductor with this resistor. Okay, and in this case, what we would say is, well, we saw that if we make the high potential side on the left, using the positive terminal of the battery, we'll get an electric field that points to the right, and negative charges will start flowing left. That means the current is flowing to the right through our resistor. And so what we get is a current flow that's looping around our circuit like so. And we have now a relationship between the 3 different quantities that we've labeled in the circuit, delta V, R, and I. Those are related through, let's see, we said R would be equal to delta V divided by I. Okay, or if you wanted to calculate the current, it would be delta V divided by R. Okay, so in lab number 4, you will investigate how the resistance of a wire depends on its diameter D. And so here's going to be our diameter D. And so you'll have always the same type of wire made of the same material of the same length. We'll just change the diameter and we'll look at how that resistance changes. So you'll measure, you'll provide a delta V, you'll measure the current, you'll take the ratio of the 2 to find R, and we'll see how R changes when we change that diameter. Okay, so the other thing you'll do is you'll do an equivalent experiment using these hydraulic circuits that I was talking about. And so we're going to use for our water current, we're going to measure the volume of water that crosses some surface per unit time. The way we'll do it is we'll actually collect the water in a little beaker and measure. Sorry, do you have a question over there? You have a question? No. All right. So we'll collect water in a little beaker and measure its mass. And knowing the density of water, you could then calculate the volume. And so you figure out how much volume is collected in the beaker in a given time interval. And so that volume divided by delta T will be our water current. Okay. Once you know the water current, well, what drives the flow of water is a pressure difference. And so we're going to calculate the pressure difference across our little tube that we're flowing the water through. And if you know the pressure difference and you know the water current, you can calculate an effective resistance as instead of delta V over I, it'll be a pressure difference divided by the water flow rate. And then we'll see how that resistance changes as we change the diameter of the tube that the water's flowing through. And so you could probably guess, what would you expect? Would you expect the resistance of a large diameter tube to be less than, equal to, or greater than the resistance of a narrow tube? What do you think? Is it easier for water to flow through a fat tube or a skinny one? A fat one, of course. So hopefully what we'll see is we'll get some kind of analogy between the electric circuits and the water ones. And so it might lead to some new insights where if we get higher rate of flow through a fat tube for water current, maybe we also get a higher electrical current through fat, thick diameter wires than we do through skinny ones. And so that's what lab 4 is about. Okay, good. So what I want to do then is I want to go back to capacitors for a second, because there's one more topic that we need to cover about capacitors. Okay, so let's go back to capacitors. So what you might run into is maybe you're in a lab and you're designing a circuit and you need a certain value of capacitance. And so you look around in the drawers and the cupboards and you find all the capacitors you have, and none of them are the right value that you need. So what we're going to talk about is combining different capacitors, combinations of capacitors, to make new values of capacitance. So combinations. Oh, that's good. What happened here? So screen sharing ended. Let's see if we can get that back. Okay, so combinations of capacitors. What I'm going to do is I'm going to give you the results, and then we'll go through and we'll see if we can prove them or show where they come from. So there's really two ways to combine capacitors. So there's parallel combinations, where what we'll do is we'll put a bunch of capacitors side by side. I'll draw 3 of them, but there could be as many as you like. So you put them side by side, and then we're going to take all the top plates and we're going to connect them together. And so we'll connect them together with wires like this. Maybe this one is C1, this is C2, and this is C3. And so we take all the top plates of C1, C2, and C3, and they're all connected together. And then we do the same for the bottom plates. And so here we go. So we connect them all together. So we connect together all top plates and all the bottom plates. And the idea is we want to represent that combination as a single equivalent capacitance. So will be C equivalent. So we want to represent the parallel combination as a single equivalent capacitor. Capacitor, and we'll call that C equivalent. By equivalent capacitor, what I mean is if we took a set of parallel, we take a bunch of capacitors, put them in parallel, and then we put them in a circuit. Maybe we attach them to a battery and we store a certain amount of charge. What we require for our equivalent capacitor is that if we connect it to the same battery, it will store the same amount of charge. So it does the same function in our circuit. So for parallel capacitors, the result is that C equivalent is just the sum of the individual capacitors. So C equivalent is given by the sum of each of the parallel capacitances. Okay, there's one other way to combine our capacitors, and the other way is a series combination. So in this time, instead of putting all our capacitors side by side where all the top plates are, say, at the top of the page and all the bottom plates are at the bottom, what we're going to do is we're going to line them up in a row. And so we'll take our capacitor, here's C1, we'll take, here's C2, and then here's C3, like so. So C1, C2, C3. So in a series combination, we're not connecting top plate to top plate and bottom plate to bottom plate, but the way I've drawn it here, I will take the, say, right plate of C1 and connect it to the left of C2, and then the right plate of C3 and connect it to the left plate of C2. And so what we'll do is we'll join them up in this way. So what we're going to try to do is represent that combination as a single C equivalent. Okay, so in a series combination, we line up capacitors and connect, let's say, nearest plates to one another. So of course you could have like more complicated combinations of capacitors, but they can always be broken down into some arrangement of series and parallel capacitances. So if we know these two rules, then we could deconstruct any complicated, any combination of capacitors, no matter how complex you want to make it. Okay, so in this case, we will find that we had for parallel capacitors that C equivalent was just the sum of C1, C2, C3. For the series case, it's actually the inverses that add. So the inverse of C1 plus the inverse of C2 plus the inverse of C3 is going to give you the inverse of C equivalent. So it's 1 over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C equivalent. So the inverses of the individual capacitances add to give not C equivalent, but the inverse of C equivalent, to give the inverse C equivalent. So if we come back and think about our original motivation, like we imagined we're in a lab and we have all these capacitors, but none of them are the right values. If we wanted to make a larger capacitance, we would connect them in parallel. And then, so if we connect like, 1 farad in parallel with 2 farads, that will combine to give us 3 farads. So we get a larger capacitance. It turns out for this series combination, the equivalent capacitance is always smaller than any of the individual capacitors, C1, C2, or C3. So in the series combination, let me put this on the next page. That'll be a bit better. In the series combination, it will always be the case that C equivalent is going to be less than each of the individual capacitors in the series combination. And so we can just do some mental math to try to confirm that. Let's imagine we take 2 capacitors and we put them in series. So let's take 1 farad capacitor in series with a 2 farad capacitor. So we have to add them in inverse. So 1 over 1 is 1, plus 1 over 2 is 1/2. So we get 1.5 when we add them up. 1.5 is the same as 3/2. That is equal to the inverse of C equivalent. And so we have to invert that to get C equivalent is going to be 2/3, 0.667. 0.667 is less than the 1 farad and the 2 farads that we started with. So if you're in the lab and you need to make a larger capacitance, you should connect individual capacitors in parallel. If you want to make a smaller capacitance, you should combine the individual capacitors in series. Okay, so we probably have time to verify the parallel combination. And so let's do that. Let's go back to a parallel combination of capacitors. Okay, so what we'll do is we'll take our 3 capacitors, like so. We'll hook them up in parallel, like this. Okay, so this is going to be C1, C2, and here's C3. And in addition to that, we'll connect them to a battery. And so that battery provides a voltage difference, delta V. Okay, so what I want to recognize is that what we have are capacitors are made out of these conducting plates, right? These 2 parallel plates that are conducting. And then we're going to make our parallel combination by taking conducting wires and connecting one top plate of one capacitor to the top plate of the next one and to the top plate of the next one. And so if you think about that, what we have is a conducting plate connected by conducting wires to the next conducting plate. And then another conducting wire that goes to the 3rd conducting plate. And so these are all the top plates in this case. And if we connect it up like this, everything that I've colored red, in fact, we could take the other wire that goes to the positive terminal of the battery, everything that I've colored red is now one single conductor. They're all connected together by these wires. So this is one single conductor. And then I can, of course, do the same thing for the bottom plates. This bottom plate is connected to this one by these conducting wires. And it's also connected to this plate at the bottom by that wire. And then that goes to the bottom terminal of the battery. Okay, and so here is another single conductor. Okay, so if we did this, if we started with, say, our capacitors uncharged, and then we built this circuit, then these capacitors will charge up to some value. They'll each have some value, say Q1, Q2, Q3. But after they're charged, there'll be no more flow of charge, or the charge won't flow anymore. And if there is no net flow of charge, we have conductors in equilibrium. So after the capacitors charge up, there is no more flow of charge. And that means our conductors are in equilibrium. And one of the things we said about conductors in equilibrium is that the potential everywhere on that conductor is going to be the same. So if I look at the top plate of C1, it has to be at the same potential as the top plate of C2 and the top plate of C3 and the positive terminal of the battery. So that means all, let's see, maybe I could say then each conductor is at a uniform or constant potential. Okay, and so we could say the red one is going to be at some potential VA, whatever that is. Okay, it's whatever the potential that gets set by that positive terminal of the battery. And then the blue one is also at a uniform potential, it's VB, and that's it. So the bottom plate of all the capacitors are all at the same potential VB. So therefore, the top plates of each capacitor is at the same potential, let's call it VA, and bottom plates are all at the potential VB. So that means if I was to calculate the potential difference across each capacitor, they would all be exactly the same. It would be VA minus VB. So therefore, the potential differences, potential differences across each parallel capacitor is the same. So we would say that the potential across capacitor 1 is equal to the potential across capacitor 2 is equal to the potential across capacitor 3, and that would all just be equal to VA minus VB, whatever that is, just the voltage difference provided by the battery. Okay, so fine, that's fair enough. So let's just call this delta V. If all the voltages are the same, then we don't need subscripts to distinguish them because they're all identical. And this delta V is just whatever the delta V of the battery is. Okay, maybe it's 9 volts or something like that. Okay, but recall, by definition, capacitance is charge divided by delta V. So if they all have the same delta V, what we could do is we could use that to solve for the charge of each capacitor. So Q is going to be C delta V. So delta V is always the same, but our capacitor C1 and C2 and C3, they may have different capacitances, so they'll get different charges. So we'll say Q1 is going to be equal to C1 delta V. Q2 is going to be C2 delta V. Q3 will be C3 delta V. And we could go back and we could we could draw that. So this would be plus Q1 minus Q1 plus Q2 minus Q2 plus Q3 minus Q3. Okay, so that means the total charge across our parallel combination is Q1 plus Q2 plus Q3. So therefore, the total charge Q across, or let's say stored by the parallel combination is at Q, well, it's just the charge stored by each of the capacitors. But Q1 is C1 delta V, and Q2 is C2 delta V, and C3 delta V is Q3. Of course, all the delta V's are the same, and so we could say that the total stored charge is going to be the sum of all the capacitances times delta V. Let's call this equation 1. Okay, so we have about 4 minutes left. What we want to do is we want to represent that parallel combination as a single equivalent capacitor. So if I was to draw the parallel combination again, we would have C1 and C2 and C3. So C2, C1. And what we want to do is we want to represent that as, we're going to use the same battery, but this is going to be C equivalent delta. And so C equivalent is going to store some charge. It'll be plus Q equivalent and minus Q equivalent will be stored on the top and bottom plates respectively. And we would say for C equivalent, the stored charge is Q equivalent. Well, it was just C times delta V, right? So it's C equivalent times delta V, where delta V is the battery voltage. We're using the same battery. Well, in order for these two circuits to be equivalent, they must store the same charge. So C equivalent must store the same total charge. Otherwise, it wouldn't be called an equivalent capacitor. And so therefore, Q equivalent is equal to Q, and that has to be equal to C equivalent delta V. And so we'll call that equation 2. Oops. And if we compare equations 1 and 2, there are two expressions for the same quantity, the total stored charge. And so they must be equal. Okay. So equations 1 and 2 each calculate the total stored charge Q, and they must be equal. So if we say 1 is equal to 2, what we get for equation 1 is C1 plus C2 plus C3 times delta V is equal to equation 2 is C equivalent times delta V. We use the same battery in the two circuits, so we get the same voltage difference. That cancels. And so therefore, C equivalent is equal to C1 plus C2 plus C3. And that is our expression for parallel capacitors. Okay, so Wednesday is the midterm, then Friday we'll do the series combination of capacitors. That's what we'll start with. All right, thanks very much.